So, in the previous class, we were discussing about the concept of soft margin. Hard margin, we have worked and we have derived the formulation for hard margin. But in case of soft margin, we have seen that every time it's not a case of linear separability. Okay, it's a simple case, linear separability, and our data set is not most of the time is linearly separable. So what can be done in that particular case? Linear margin has been not much supported. Okay, so using that concept only, we have seen that you can apply some parameter, some error to the equation which we have generalized in case of hard margin. So this is the diagram which we were discussing previously, that sir, you can allow the misclassification of the data points, and according to the misclassification you can allocate some penalty. Okay, so what we studied in the previous class, these are the basic concepts, and here is the problem statement. Okay, for example, your data points are organized in such a way and you need to separate it, and if you make a line, obviously there will be many more misclassifications being present here. So what can be done? What is the choice? So here we were talking about the short margin formulation. Okay, that means we have been told that allow SVM to make a certain number of mistakes and keep the margin as wide as possible so that other points can be classified correctly. Okay, if some of the points are creating an issue, they have been misclassified, don't worry, but try to make the points which are being separable with a wider margin. You can do that. Okay, so what is the motivation behind this concept? The motivation behind this concept is all real world application have data that is linearly inseparable. That's the first case, and in rare case we are having linearly separable data, and we say if by this linear separability, if we can divide the data points, then it's overfitting of the model because all the points will be separated, then 100% accuracy, and it's an overfitting. Okay, so that's the motivation. We need to make a soft margin. Okay, so how to make a soft margin? For that, what can be done? Here is we were discussing in the previous class. You are available with the two margins. One is the green margin, one is the red margin, and you have been given a choice that if you make a red margin, okay, if you make a red margin in this particular case, obviously, I guess there is no error, there is no fault. Green and red both are good separated. That means you are having the fine separability, nothing is missing here. Okay, no mix up, and 100% accuracy. However, if you select this green margin, so one green point is being misclassified here, you can see. And now you have been asked that what is your choice of selecting the margin, either green or either red. So according to the discussion and as per the suggestion which came up, which is better, red or green? Okay, so here the decision boundary made by red perfectly separates all the training points we have seen. However, it is really a good idea to have a decision boundary with such less margin. That's the question. Can we reduce the margin? Because you can see that this margin, red, is been closer to the data points. Okay, so is this a good idea to create such kind of margin? Then if we select this green one, so this green one, this particular margin is been far away from red points also and green points also. However, there is one issue that a green point is being misclassified here. Okay, one point is misclassified. According to the basic concept which we have studied in the previous class, that equation we have derived, we have been told that, sir, we need to make a margin wider. That's the primary concept. Okay, so if you think that such kind of decision boundary will generalize well on unseen data, the answer is no. Okay, the answer is no for the read decision boundary, because when you make a decision boundary closer, it is been violating our general generalized formula rule on which we have derived that margin should have to be wider, but here the margin has been closer, it's not wide, so it's violating that rule. So we are saying no, this kind of margin is not good. Then what is good? The green boundary has a wider margin that allows it to generalize well over unseen data. Okay, that's what we have derived. We have generalized equation, and according to my equation, when I fit the data points into it, this green margin is going to work me better. However, there is some issue with this green margin is the misclassifications. There's a misclassification, but it will help you in avoiding overfitting problem. Okay, it will give you misclassifications, but it will help you in avoiding your overfitting problem. Okay, and when we were studying primary, we have seen that margin, there could be many margin created to separate the classes. Okay, for example, this is class A and this is class B. We have seen we can separate them by this margin also, we can separate them by this margin also, but we have studied that the margin should be somewhat compatible distance from the data points, it should be more. Okay, so this is also correct, but the point is I will be selecting this margin because it's been far away from both the points. Here also the same thing happened. As per our general equation, green should be something which we are going to select to avoid the overfitting. Now, you have been told, okay, you are selecting, but for selection, there is a misclassification. So, for the misclassification, you will be given penalty. Okay, so what can be done? What can be done? Here's the maths which we were discussing in the last class. The equation which we have seen for the hard margin is L equal to 1 by 2 W square. Okay, for this thing na, we were solving. Okay, but now we are adding one more term C, that is called as a mistake. Okay, number of mistakes which you are going to make. Okay, so this C is an hyperparameter. We did discuss in the previous class that C is a hyperparameter that decides the trade-off between the maximizing the margin and minimizing the mistakes. Okay, we have to maximize the margin also, but we need to take care that errors should also be less, mistakes should also be less. Okay, so when C is small, when your value of C is small, that means classification mistakes are given less importance and focus is more on maximizing the margin. That means I'm keep on maximizing the margin. Okay, and I'm literally avoiding that how many mistakes I'm making. But during the same time, okay, if you made some mistakes, few mistakes, that is okay, but when you are continuing making the mistakes, many mistakes, then obviously you are having the kind of classification which you are doing with the SVM. Obviously this SVM algorithm is going to crash. Why? Because there are many mistakes you have done. So how you can get a perfect classification? Perfect, not overfitted. Okay, perfect, that means you should have notable accuracy. Okay, not 100%, not 99%, but at least some good choice of accuracy you should be having. So here they said value of C, if it is been small, if the value C is small, that means you are doing the classification, and you are the classification, you are avoiding the mistakes, less importance given to the mistakes, and your focus is to make the margin wider. So making margin wider. And whereas when C is large, that means when your focus is no, 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 my mistake should not be that much. I can reduce the size of margin. Okay, but don't do much class miss class. That means if C is okay, that means you're saying C is large. The focus is more on avoiding the misclassification. You don't want to misclassify. Okay, then you have to compromise with the margin. Margin should have to be less. That means your margin will be going closer na, to the data points. Here your margin is going far away from the data points. Here your margin is going closer to the data point. Same case, you can see in red line. In red line, my margin M1 is closer to the data points. Here I am not making any mistakes. So closer, small, margin is small. So mistakes you are taking care. Here in case of green, this is second margin. You are making your margin wider, but you are having a mistake that one is misclassified and it will be now considered into the red side. Okay, but here if you continue this thing, and if more and more green points are been getting misclassified, that's what they told, it's a trade off between the margin and your this errors. Margin and the error, it's a trade off between these two. Okay, so in this particular case, we have to be cautious, because as many points will be misclassified, you have to go into compromise with the accuracy. Okay, what they further said, now as you've seen, this is the math, this is your hard margin, but now I'm allowing mistakes also. Fine. If you proceed ahead, if you proceed ahead, okay, so the point is, you can consider the misclassification points also. What is the distance from the margin which you are selecting? That is also one issue. So in the previous class we were here and we were talking that at this point we should note that however not all mistakes are equal. There is one more thing, you are making mistake is okay, but not all mistakes are equal. Some are bigger mistakes, some are smaller mistakes. Now how we can say bigger and smaller mistake? By seeing this diagram we can understand that, for example, this is your hyperplane, this is your hyperplane, okay, and you are performing the classification. Okay, this is your decision boundary, this green one is a decision boundary. Okay, so this red point is misclassified. It should have been present here, but it came here on the left side of the decision boundary. So we need to calculate the distance of this red point from my this particular line. Okay, from this line. Okay, so what this line actually means, what this line actually means here, because I need to make a plane. Okay, here is a plane. Okay, so the line where I can consider the support vectors, till where I can consider the support vectors, I'm going to calculate the distance. Okay, so the red point which has been misclassified, I need to calculate the distance from here. Okay, and now similarly, I need to calculate the distance for the green, which is misclassified. So green is also misclassified. So from the green boundary, I need to calculate the distance. So you can see the distance of red, which is misclassified, is been less, and the distance of green, which has been misclassified, is been more. Okay, so this is this is also an error. This is also an error, but it's a small. This is a small error, and this is large error. Okay, this is the way which we can say small and the large errors. Now, what can be done ahead? The penalty occurred by the data points for being on the wrong side of the decision boundary. So, what they are saying next? They are saying that the idea is for every data point, you have to introduce a slack variable. This is slack variable. For every data point which has been misclassified, you need to introduce the slack variable. Okay, and this value is the distance of xi from the corresponding class margin. Okay, so you are having class margins. These lines are said to be the class margins. This is your class margin for green, and this is your class margin for red. Okay, so accordingly, na, I need to take care of it, of these class margins. Okay, then what is the equation? What is the equation we are going to use it? Thus, the points that are far away from the margin on the wrong side would be get more penalty. Okay, as much as the distance, as much as the penalty you have to apply. Here is the formula. With the idea of this, each data point xi needs to satisfy the constraint. Now we have changed the constraints. This was your equation till here when you were considering the hard margin, but now you have to introduce a slack variable also. One more variable introduced when we are working with a soft margin, and this is your error penalty you have to impose. Now, the left hand side of the inequality could be thought of like of the confidence of the classification. This is the confidence of classification. Confidence score greater than equal to 1 suggests that classifier has classified the point correctly. Okay, so here they said that you have to consider this as a confidence score, confidence. Okay, on the left hand side, left hand side is a confidence. Okay, so this is your confidence, left side. Overall, it's an inequality, we very well know, and we have used this inequality in solving our equation. Okay, with Lagrange. All right. So they said a confidence score greater than equal to 1. That means you are having a good classification. And the confidence score less than 1, it means the classifier did not classify the points correctly, and you are going to give the penalty. They are going to give the penalty. So, if we see this equation only, if we see, obviously, whatever the statement written now, it's looking absolutely clear. You can understand how this will become greater than 1. How this will become greater than 1? How? If your error is less, or if error is equal to 0. If your error is equal to 0, so 1 minus 0 is 1. 1 minus 0 is 1. Okay, so obviously the value which I am going to obtain from here, if it is greater than equal to 1, that means you have correctly classified. But if you are having errors, if they are more, okay, then and if it's going to be negative, so this is the inequality, it will change its sign with respect to minus. So that's what they told. If the confidence score is less than 1, then obviously you are performing misclassification and penalty is more. So penalty 0 means no misclassification, it's working fine. But if penalty is greater than 0, okay, so as much as penalties are, so you this value will going to rise, and if this value is going to rise, it will be negative, and when it will be negative, it will revert the sign. So your confidence is less than 1. So that's what they said, misclassification. Okay, so it's a
But
huh.
he is not clearing the one things
Hmm,
for the high margin.
hmm.
It's not mentioning. Are we capturing the high margin or not with this statement?
We are capturing the high margin or not with this
With
statement.
this statement, with this statement, we're clear that
Hmm.
our error is expected to have the zero.
Huh. Now
Yeah,
expected is 0 according to the
yeah,
hard margin. It
yeah.
needs to be expected to be like 0. Okay, but the thing is, if it is not been 0, that means you are having the penalty. Okay, so that's what we called it as the slack, and you can understand by slack here they mentioned about it. Okay, what they mentioned, there's a slack variable, this thing ei, the value of ei is the distance. Okay, it's a distance. So when this is a general equation, I will consider one point by one point. You can see now, xi yi. Let us consider point by point,
Yeah. Yeah.
and put the value here. What is the error? है ना, point by point we are
mm,
going to
mm.
consider. Okay, and accordingly I need to put as, and it's already told that if it is far from the boundary, okay, from the class boundary, obviously this ei is with more, that how much far it is, you need to put the value, how much far it is. If it is very much far, okay, so obviously more is the penalty. See, the thing is, if it is misclassified 101%, you need to pay, penalty is there. But only the point is, if it is not that much far, then less penalty. If it is more far, then it is more penalty. So ei is been the distance, ei is the distance of xi from the corresponding class margin, that's it. So here I need to put the distance. Okay, so previously in our general equation, in case of hard margin, okay, so till here we have understood that this is the equation for the hard margin. Okay, and we are saying that our data is already linearly separable. We are already considering the filtered case. In case of hard margin, we are already considered a filter case. तो वो तो overfitting था, वो तो वैसे ही था. Okay, अब here we are not considering the filtered case. Here we are considering inseparable, linearly inseparable case. So the thing is, we have to introduce, we have primarily introduced this variable, and we are saying यार गलती तो होगी. जब आप बोल रहे हो it is linearly inseparable, that 101%, 100% damn you are going to make a mistake. So kindly consider this variable also, पहले से लेकर चलो. Okay, so how I can say that, for example, if we are driving on a road and obviously you are not wearing a helmet, so that's a mistake, है ना? But still we take a chance, chalo let's drive. Okay, but however when you are going to encounter the traffic police, then you have to give the penalty as many as times you are going to. तो ये तो पता ही है कि we have chosen this thing. So that's what they have mentioned ei. Okay, and is anything more present here in the comment? Okay, yeah. Any further doubt? Please let me know.
Yes, sir. I want to ask
Hmm.
how we are finding the confidence score.
How we are confidence
Yes,
score, no?
how
Ah,
we will
see,
calculate. Like the
confidence is.
predict over
Hmm.
or the something else we are doing.
See, we are putting the value of distance here. Okay,
Okay.
we are putting the value of distance of that data point. Okay, if it has been misclassified, if it is obviously, if it is greater than 1, if it is greater than 1, okay, so for example 2, distance is 2, let us suppose. So 1 minus 2 is equal to minus 1, it is negative, है ना, it is negative. So they said confidence score greater than equal to 1 suggests that the classifier has classified the point correctly. Okay, so overall the left hand side of the inequality could be thought of the confidence classification. They said this is your confidence classification, this is your confidence classification, they are saying overall. Okay, so here if you get negative value, that means obviously it's a misclassification. Negative means misclassification, so your confidence score is less than 1, that's what they are saying. And if you are not having any misclassification, obviously it is greater than equal to 1, quite clear. Okay, so greater than equal to 1, that means the classification has classified the point correctly, that means your error is 0. So if error is uh, till 1, for example, if the distance of error is still 1, okay, I can have, I can manage something. Okay, but when it's going to increase, the distance is going to increase, obviously it's a misclassification, then they are saying okay, now the score is less than 1. Okay, so it does not classify properly, it's quite clear from this thing only. Okay, so if it is 0, then you are having greater than equal to 1, and if it is not 0, if error is there, something present, so obviously this value is going to be less than 1. If it is less than 1, if they are saying overall this is a confidence score. Okay, if it is less than 1, that means the classification does not classify the point correctly, that's it. Yeah, any more doubt, please let me know if you understood or not.
No, sir. No, it's clear now.
Okay, so confidence has been set to this equation. Okay, so we are adding penalty now. What they did, given these constraints, our objective is to minimize the function now. Ab See, previously we were having this thing only in the hard margin, and we have performed Lagrange over till here, है ना? We have performed Lagrange. And what was the theme of Lagrange? The theme of Lagrange was, if we want to solve any objective function, this is your objective function. This thing is your objective function. So they said, if we want to solve any objective function over a constraint, so this was your constraint. So you need to multiply this constraint with the Lagrange multiple lambda I. This is what we have seen in the previous classes. And you need to add this thing to your actual objective function, and then you need to partially differentiate it. W partial differentiation with respect to lambda partial differentiation with respect to biased partial differentiation, equate all those things to zero. And there are two possibilities which you have learned. One is your primary optimization, and second one was dual optimization. When you are not going to get the answer from the primary, then you need to proceed ahead with the dual optimization, and we have did this thing in hard margin. We have proceeded for the dual, because from primary we haven't got the answer. That's why we have resubstituted the value of W in the same equation. I hope you remember previous class. Okay, so dual optimization we have performed. Okay, so now what changes we have seen in this particular equation for the soft margin? What happened in this soft margin? This term is present. C is the number of mistakes which you are doing, and summation I slack I, obviously it's a distance of every mistake which you have done. So I need to take the summation for each and every data point. That's what I have to do. Okay, and then this term is again same, summation I and lambda I, yi, and all these things are same till here, plus ei slack I. I'm adding here also slack I. For every data point I need to add slack. That's what I have to do. So this is this equation is your hard margin. We have already uh, performed the complete derivation of this hard margin in the previous classes. Okay, but now in case of short margin, you are adding a slack term also, error term also. Here also, and here also you are adding the slack terms. So C is your hyperparameter number of, okay, times you are making the errors. Okay, and this is your error value, distance. Same thing here as a distance of the misclassification. Okay, so this is linearly separable, and this is non-linearly separable equations. Now what can be done ahead? We can see ei term are extra in the modified objective, and everything else is same. Yes, we very well know about this thing. So point to be noted, in the final solution, lambda is corresponding to points that are closest to the margin, and on the wrong side of the margin, that is having non-zero slack I, would be non-zero as we play a key role. There are many things they have written. Okay, so now from this point, what is being trying to explain uh, to us? They are saying lambda is corresponding to the points that are closest to the margin. This lambda is Lagrange value. Okay, so it said that lambda is corresponding to the points which are closest to the margin and on the wrong side of the margin would be non-zero, as they play a key role in positioning of the decision boundary. So yeah, the thing is key positioning of the decision boundary, lambda is playing an important role. The positioning, how we have to define the positioning of a decision boundary, how we are going to define the positioning? We said, sir, margin should have to be more, but take care of misclassification also. Both are in versus in fight with each other. Okay, so lambda is something, that's what they said, point to be noted. Lambda is corresponding to points that are closest to the margin. Lambda, the value of lambda should corresponds to the points which are closer to the margin, and on the wrong side of the margin would be non-zero. as they play a key role in positioning of the decision boundary, essentially making them the support vector. So when if obviously if there is a misclassification, and we have seen that how the support vectors are marked. Support vectors are marked, you very well know about these things, that this is your class A, this is your class B margin, so these are the support vector. Okay, so they are saying that value of lambda is going to help us for the data points which are closer to the margin, and we can assign them. How we can assign them as a support vectors? Okay, how we can assign them as a support vectors? And we can say, yeah, now we are having a decision boundary, this is your decision boundary, and these are your class margins. Okay, so accordingly we will calculate. Okay, for example, this is class B, any point which falls here of class B, this is the distance of error. If any point of class A, if it falls here, so this is the distance of the A from the class margin A. So these points are misclassified points. So that's what they are saying. In general terms, they said the final solution lambda, the finals whatever we are going to solve. For example, the same which we solved previously. Okay, same thing here for this equation. Same thing here for the equation, that we need to differentiate it with respect to w lambda and b and equate it to 0. We are going to get some values out of it. However, we are not going to do, but the thing is we should be knowing what's happening. Okay, so accordingly they said whatever be the lambda of value of lambda which you will achieve after solving the equation. Okay, so that corresponds to the points which are closer to the margin. That should be these points which are closer to the margin. Okay, and then accordingly what you have to say, we have to decide the support vectors, and they will play an important role in positioning of the data decision boundary. Okay, so with the help of this lambda value only, now we are going to get, these should be supported, because there is a question came, sir, how you can make a support vectors, whom data points you are going to say support vector? This could be also a question. Okay, so support vector will be made according to that, which what should be your decision boundary. Okay, what should be your decision boundary? Accordingly we have to decide that, okay, these are the support vector and these are not the support vector. So everything is being mathematically drawn, then only the decision boundary, support vector, margin, misclassification, everything is being put up here. Okay, so however we are not going to solve this particular equation. We have already solved for the hard margin. However, similar solution will be uh, done here. I was also doing the hands out. Hopefully I will share the handout soon for the hard margin solution. Okay, so you have already present, in those who are already present in the previous class, they have seen the derivation. So this derivation which I have done, I will share the handout so you can have a recall how general equation has been achieved. Okay, now what's next, what they are trying to say next? Kernel trick. Again, it's a very important concept, kernel trick, to tackle the problem of linear inseparability. So we achieved this equation. So far we have achieved this equation of linear inseparability. Okay, that's why they mention L, linear inseparability. Okay, now what can be done? So kernel functions are a generalized function. So we are having kernel functions now. Okay, kernel trick, for kernel trick we are having kernel functions, and we have seen this different types of kernel functions when I was teaching SVM introductory class. You have seen radial bias, etc., etc. There are various kernel functions which are available. Okay, so kernel functions are generalized functions that take two vectors of any dimension as an input, and output us and output a score that denotes how similar the input vectors are. Now what does this mean? They are saying that accept the two vector as an input and output the score that denotes how similar these two input vector are. That means I am checking the similarity of two vectors. Similarity of two vectors I am checking. So A simple kernel function, you already know that a dot product function. If the dot product is small, we conclude that the vectors are different, and the dot product is large, we conclude that the vectors are more similar. Now, what does this mean? What actually this means? Two vectors, if the dot product is small and dot product is more, then they are similar and not similar. What this means? We need to crack this concept, because kernel is important term here. Okay, and in case of kernel trick, what we studied, that sir, when you are having a problem of linearly inseparable, then you need to make, or you need to add a dimension. You need to add a dimension that will shift the data points over that particular dimension, and it will separate your data points, which has been not separated by a line or a plane. Okay, so you need to shift the data points accordingly. And we have seen various kernel functions when I did talk about in the introductory class, and then they are saying that the kernel functions are generalized functions, and they take input as a two vector, and they are checking how much similar they are. And similarity, they are saying ki the similarity, they are saying when we take a dot product. Okay, and the dot product is small. If the dot product comes to be small, then we conclude that okay, they are different from each other. And when the dot product is more, then they are more similar with each other. So I think we have to explore more about this concept, kernel function. Let's see how the things come up ahead. The trick. Let us look the objective function for the linearly inseparable case. Huh? In the previous lecture, your trick came like this: lambda summation lambda I minus 1 by 2, these terms were present when we perform dual optimization, and we have put the value of w in the same equation, and we have substituted the values also, that is lambda I yi, this is equal to 0, we were present with that. And the value of w was lambda I x I y, something was there. Okay, and we have put in the equation of hard margin, that the generalized equation, and then something like this came as a result. Okay, so they said, let us look at the objective function for linearly inseparable case. So it's mandatory for those people who haven't attended the previous classes. Daily there is a discussion of this equation based upon SVM has been going on. Okay, because the math is not that much simple for the SVM. We have to consider various cases. Okay, so accordingly you have to talk about and understand what's happening. So this is the objective function which we have achieved in linearly separable final equation which it gave to us. Okay, and here in the previous class we did told that means we need to do some efforts from our side, because we are having lambda j also, yj also. So these terms are a bit confusing, because we started with lambda I xi yi, and then he also introduced lambda j yj and all these things, so a bit confusing. So we have to do some our handout, and we'll check that how things are coming. Okay, we have already discussed in the previous class. So they said, okay, this is certainly an equation, and what next? This is modified form of the objective equation. Here we have substituted the optimal value w and b, everything we have done. The optimal values can be calculated by differentiating, everything we have done already. Then afterwards only now we got this particular value after complete solution, dual optimization performance. We got this result by putting all the values w and etc, what we want to do, we have done. What's happening next? We can observe in equation 5 the objective function depends on the dot product of the input vector xi and the xj, okay, which is nothing but a kernel function. Okay, xi and the xj, these are said to be the kernel functions. Okay, can we get this equation again? Here we are having xi vector and the xj vector, xi and the xj, these two vectors we are getting. Okay, and they are saying that it's a dot product of two vector, that is why it's a kernel function. So kernel function is a dot product of two vectors, and it can have a minimum value, it can have a maximum value. We are trying to understand some concepts here, okay, what it is saying. Fine. So the thing is, let me reshare my screen and we can have some rough uh, solution also, that what it's trying to say, x1 vector and the x2 vector. Let me share my entire screen and let's try to understand what's happening. Okay, so if I would say x1 and x2, how we got these values x1 and x2? We started from yi w xi plus b minus 1, and we are having w square by 2, okay, and then we are multiplying by lambda also with this particular equation, okay, followed by minus sign. This was our hard margin equation. This is your objective function, and this is your constraint multiply by Lagrange. We were doing this thing, okay, and then we equated it to, okay, this was your L, and then we perform partial differentiation and put the value of lambda, and then again into this equation, and whatever be the solution which you are seeing here, it's a result or outcome of that only. Okay, in the previous class we have already talked about, this is the result which you are getting. Okay, so here they are saying xi is a vector. This xi is a vector thing. Okay, how this xi become a vector? How? If we think how we have started the derivation of support vector machine, what was the initial steps for the derivation of support vector machine? It has been told to us that y equal to ax plus b. We started with a linear equation only, and then we switched y here and we told ax minus y plus b equal to 0. Then it has been told to you कि आप you do one thing, x को x1 बोलो, and y you should y you are saying कि x2 बोलो. These are the two एक point है. Let us consider x1 and x2. These are 2 points. They are represented by x and y. So put it here. So then you put here. तो ये a x1 minus x2 plus b equal to 0, and then you have modified like this, x1 minus 1 dot x2 plus b equal to 0. That's what you have done. And then we have already discussed कि सर ये तो dot product आ रहा है. Sir, this is a dot product. Between whom? It is a dot product between x1 x2 and a minus 1. So ये x1 x2 I can write it like यार this is capital X. It can be written like okay x1 x2, and ये जो a and minus 1 है ना, it can be written like a weight. तो ये a minus 1 something like right. तो इनका dot product है. तो a x1 a1 minus x2 into minus 1, like if I can take the dot product of these two, okay, wx if I write the x whatever you want to say, okay, this equation can be remodified as, and it can be written like this, wx plus b equal to 0. So let us write wx. If I take the dot product of these two na, I am going to get this equation, and you say that this is the equation of hyperplane h naught. और फिर आगे, and what was our next after that? This is the equation of hyperplane. Then next you have been told ki let us suppose you have been told in the further case you are having two hyperplane, एक minus 1 and then you are having a plus 1. So these equations only you have what, where are the equation? These equation, this equation only you have modified and you have written wx plus b is greater than equal to 1 if value of y is plus 1, and wx plus b is less than equal to minus 1 if y is minus 1. And then we have combined these two equations. to solve the linearly inseparable. I have already discussed. So why plus 1 and minus 1, they are saying that we are available with two classes. Plus 1 and the minus 1, we are available with two classes. In the when I was talking initially about the maths, all these things I have discussed. So this x1 and x2, actually this it's a vector. They are saying that it's a vector thing. Okay, I going to represent the point this xi, and they are saying that it's certainly a vector. So we are available with the two vectors, they are saying, xi and xj. These are the two vectors we are available with. And they further said it's a product of two vector, and the product of two vector, we are saying it's a kernel function. Again, they said it's a kernel function, product of two vector. So that's why now they clearly indicated this thing, x vector, xi vector and xj vector, they indicated this thing. So it's a product of two vectors. Okay, so what will happen, what will happen further? These values can be calculated by different, हाँ ये तो कर दे, already we done, हाँ. We can observe the equation 5. The objective depends upon the dot product of the input vector xi and xj. There is nothing but a kernel function. Now there is a good thing. We don't have to restrict a simple kernel function like a dot product. Then what we can do? Kernel function in place of dot product has a capability of measuring the similarity of higher dimension that could be much more accurate without increasing the computational cost. This is called as kernel trick. Now, अब यार ये क्या है? What it is trying to focus? High dimension. एक बात तो समझ में आई. One thing we understood कि if the data points are not linearly separable, then obviously it has been told to you कि sir, you have to add dimension, and you need to shift the data points over this dimension. Then only you can separate. Then only you can separate. Because we have seen some cases where there's a tough call for a line to separate the data. So that's why, accordingly, if you can check out the line which it has been said to you, we have in place for dot product capability of measuring similarity in the higher dimensions. Higher, what is this higher? Why this higher dimension came? The higher dimension came because we don't have any specifically only few dimension. We are having higher dimensions, and obviously we are going to add few more dimension for the separability of the data. Okay, so to add a dimension, convert a dimension into convert a minimum dimension to higher dimension. That's what we have to do. That is the trick which we have to apply to separate the data points. And they said where it could be more much more accurate, so that we can classify the data points easily. Okay, so if I do tell you about, these are the nodes which are available to me. Okay, and if I say support vector machines, okay, this is the nodes for the support vector machines. Okay, and at the last, yeah, these are some of the complex cases. Yeah, this is a complex case. So right now we are dealing with a kernel trick. So this is on 2D plane, these data points are distributed. Okay, so we can't separate it linearly. So what we have to do, we have to organize these data points on high dimension. That means we need to add one more dimension to it. Then only I can separate these data points. And they are specifying same thing. So for that they are saying कि you need to have a dot product of two vectors. Abhi internally they have something more, some in inner concepts. They are saying kernel this kernel function is a dot product of the two vectors. Okay, you are having to, and they are checking the similarity. तो ये similarity क्यों? Why we are calculating the similarity? Why we are considering the dot product of the two vectors? क्या है logic, क्या है? What's the logic behind it? Okay, and at the last, these are the kernel functions. Okay, these are the kernel functions which we have studied. Okay, polynomial kernel function, radial bias kernel function, sigmoid function, linear kernel. So this is a linear kernel, and this is a radial bias, and this is a sigmoid kernel function. Our introductory class was based upon this thing only, but we haven't discussed about the maths. And when we are discussing about the maths, then this thing again came into the picture. They are saying accordingly, according to this only, we are going to separate. So what this means? Second polynomial, third polynomial. What this means? So ये आप, you are making decision boundary ना, you are making decision boundaries here. ये तो हो गया, ये linearly separable first case, simple case. And what are the equation of these? ये रहा mathematical formula, ये linear का, this is the mathematical formula, x transpose y. And ये polynomial, this is the mathematical formula, x transpose y plus 1 to the power polynomial degree. And Gaussian, this is the formula. So that's what it's trying to say abhi in current notes which we are discussing. तो अभी यहाँ पर the thing which we want to explore more is thoda bahut we understood that we are having xi and xj, these are the two vectors. We need to take the multiplication of two vectors, dot product of the two vectors. We can have a minimum value, we can have a maximum value. If the dot product is more, then these two vectors are having similarity. If the dot product is less, then they are less similar. Okay, and then we told ki apart from the dot product there is some more concepts. That concepts is related to the higher dimensions. So in place of the dot product, the capability of measuring the similarity between the vectors is based upon higher dimensions. Okay, without increasing the computational cost. So what kind of computational cost I'm talking about? See, they are saying key the kind of data which you are here in this particular case. You can see, for example, this is the way your data points are present. And if you try to perform the separation using linear line, obviously this is going to create an issue. Okay, so they want to perform some activity over it, and that activity is being dot product of the vector. Okay, and this is how they are trying to separate and creating a new dimension. That means one dimension, they want to transform the data to higher dimension, rather than trying to put an efforts to separate it. If we put an effort to separate it without adding any dimension, without the shift of these data points to that dimension, it will be definitely an issue for me. You can understand, yeah, this diagram. If you try to classify the data points blue from red on here only on this 2D plane, obviously it is tough call. It's a tough call to separate these data points. But if you create a dimension, and try to classify it, this is an easy, and it will reduce computational cost, because here the computation will be more. It's not an easy task to separate blue from red. Here there's a big problem. But if you add a dimension, if you convert it, if you create one more higher dimension, if you then do this task, it is here the computational cost is less. So that's what kernel trick is doing. They're trying to explain.
Sir,
Huh.
I have one question.
Hmm.
Sir, while increasing the dimension, each data points will have to be assigned to different dimensions, right? Different
Different
dimensions.
dimension. Different dimension
So
we have to
how
assign.
will that be done?
See, depend upon this trick only, now. That means they are calculating the vector multiplication. Okay, vector multiplication, and how much a data point needs to be shifted. I think that's coming. Max and min. If you if
So we will see it further. I mean, through maths or
Obviously maths. See, we have to apply. Everything is been based upon maths only. Obviously, some maths will be applied here. Kernel trick is totally based upon a maths, and the kind of the kernel, and the kind of here on the basis of these equations. On the basis of this equation, we are going to make a kernel. These three are the general equations which are given to us. If you are going to make a
yes.
linear kernel, so this is the equation which you have to apply, and then you need to calculate the dot product, and whatever be you are getting according. And these are the polynomial and the Gaussian you have to
So
apply.
do you have any
Yes, yes, I am having.
any example with
Yes,
small sample
yes,
of
yes,
data?
yes. I am having some of, more mathematically. Now, I
Okay.
will explain you mathematically how this is gonna work.
Yes, yes.
Okay, because it's
Okay.
very much
Yes.
important.
Thank
Right
you.
now, we understood that there is something happening over the data points, and we are having some high
Yes.
dimension. And the thing is, why we are creating high dimension? Because it's not easy for us to separate. So we need to do
Right. Right.
something. We need to do something to reduce the computational cost also. Okay, so what is the maths? So let us suppose, what's the maths? They are saying the kernel function can be written mathematically as, let us suppose this is one vector and this is another vector, um, xi x and xi y. Okay, so kxy, this is your kernel function, and we are having xi x and xi y. So x and y are the input vector, x and y are the input vector, and xi is the transformation function. So this is the transformation which we have applied, and the transformation can be of any kind. It can be linear, it can be polynomial transformation. We have seen the equations. Okay, so we need to transform the data points, these vectors points, to some dimension, high dimension. Okay, and this denotes the dot product. So I'm going to take the dot product over these two vectors according to the transformation function. According to the transformation function, I need to take the dot product of them. In case of dot product, this xi just maps the input vector to itself. They're saying I'm mapping the data points to myself. There is a mapping. तो ये बोल रहा है कि if certainly a point is present in the 2D plane, मान लो, if any point is present in a 2D plane, so how I can put this point on a 3D plane? I need to map, because I need to transform, I need to have some high dimension. And मैं कोशिश कर रहा हूँ कि यदि ये point, if this point is present in a 2D plane, how similar point I can map that. Let us suppose this point is now present on a 3D plane. तो ये मैपिंग करने की कोशिश हो रही है. Okay, are you trying to understand what I'm saying?
Yes, sir. And sir, could you please tell once more that what is x and y here?
See, x and y, these are the vectors, na? Input vector. Okay, and
These are the data
vector is
points.
obviously I need to represent the data points by vector only. ये आपके whatever be the data points, I need to represent them by the vector. That's why na, our complete calculation we did started via vectors only. If you remember, if you remember,
Yes,
okay,
yes,
we
yes.
started via vector only. Okay, so obviously it's a vector thing. So we are representing data points via the vectors. I have already shared you one GitHub, that math support vector machine maths. However, that was a bit complicated, so I changed the notes. But there you can see they have started, and I have also explained that we did started via vector only. Okay, so I am representing the points via vector, and they are saying that you need to apply some transformation. Okay, so kernel functions are essentially take the dot product of the transformed input vector. Now let us consider a case. Okay, because the question came, sir, we want a help, some good thing. What is the way to understand? We see that there is no linear decision boundary in 2D space that could perfectly separate the data points. A circular or quadratic decision boundary can do a job. We have already seen, है ना, in this problem statement also. In this problem statement, for example, if your data points are present like this, so ये तो linearly, I can't separate it linearly. This is I can't do that. So can I make a circular boundary? If I can make a circular boundary, then this red and blue points can be separated. So circular boundary बनेगी कैसे? How? That's the question. Because line से तो नहीं हो रहा. Circular boundary I need to how? So अभी क्या लगेगा उसके पीछे? What's happening? That's what we have to understand here. Okay, so let's check here. Here is a problem statement. Key, I need to separate the green points from the red points, and this can be done via circular boundary. तो क्या करें? What input vector you are going to get? What dot product you are going to do? What is the trick you are going to apply? These are certain questions. Okay, so let us talk more. So 2D space are inseparable by circular decision boundary. By a circular decision boundary. तो अब ये क्या होगा? What we are going to do? Each point P is represented by the feature x and y in 2D space. Looking at the desirable decision boundary, we can see the transformation function xi as x square y square and square root of 2xy. Now, ये क्या है? What is this x square y square and square root of 2xy? Why this came up with such transformation? Why this kind of transformation is there for any point? क्यों आया ये? They said that each point P is represented by the feature in the form x and y. Every point is represented in a 2D plane with the help of x comma y in a 2D. Okay. Now the desired decision boundary requires a function that is circular, and the equation of a circle is x square plus y square equal to r square if you are having the origin 0 0. Okay, if the center of the circle is 0 0, this is certainly the equation of a function. So they are saying ki this is the transformation function xi which has been written as x square y square and square root of 2xy. That's what they are mentioning. अभी बोला, अभी बता रहे हैं how this came, how this came. So they are saying कि आप क्या करें, let us suppose कि you are having 2 points just right now, let us consider you are having 2 points. तो उसने बोला I need to apply this transformation function over this point and this point both, I need to apply. Okay, I need to apply the transformation. तो फिर उसने आगे they said कि हाँ तो according to my circle transformation, so circle transformation is been written as certainly like this. They mention कि x1 का स्क्वायर प्लस y1 का स्क्वायर प्लस 2x1 y1 एंड x2 y2 ऐसा करके दे डिड मेंशन, यहाँ पर ऐसा बोला, दे डिड मेंशन लाइक दिस कि यदि मैं सर्कल इफ आई एम अज्यूमिंग, तो मेरे पास इफ आई डू टॉक अबाउट द नोट्स क्या था, इफ आई डू टॉक अबाउट द नोट्स, okay sir, polynomial, fine, this is your polynomial kernel function. So I think I need to take something from here. This is the general equation for the polynomial. So right now the thing is circle we need to make. Okay, and I need to assign that circle is my transformation function, and I need to apply data points to that particular circle, and this is the equation which I'm getting. Okay, so the kind of transformation function is this, and you are putting 2 points. For example, if you need to transform the 2 points p1 and p2, so you are putting the value of p1 and p2 here, and this is how you are going to get. Okay, अच्छा ये भी क्यों आया, ये भी how this appeared, how this appeared. तो for example, I can say now how they are written x square y square square root of 2xy, something like that they are writing. Okay, so if I am having x1 y1, okay, so x1 y1 can be written as in a vector notation. How we can write x1 y1 in a vector notation, x1 y1 in a vector notation, if we are having circle of equation, for example, it is given to us x square x square comma y square comma square root of 2xy ऐसा दिया है आपको. तो x1 y1 can be written as x1 का स्क्वायर comma y1 का स्क्वायर comma square root of 2x1 y1. so ये पॉइंट नंबर 1 के लिए हुआ. दिस इज फॉर पॉइंट नंबर 1. पॉइंट नंबर 2 के लिए क्या हुआ, इफ आई एम हैविंग पॉइंट नंबर 2, सो आई कैन से x2 का स्क्वायर comma y2 का square comma square root of 2 x2 y2. And if I'm going to make these three as a vector, for example these three as a vector, so I can say point p1 vector is represented by x1 का square I cap plus y1 का square j cap plus I can write 2 under root 2 x1 y1. Point p2 can be written as x2 का square I cap plus y2 का square j cap plus under root of 2 x2 y2. And then if I take the dot product of these two, if I take the dot product of p1 and the p2, obviously the equation which has been shown to you here, ये जो बताइए इसने यहाँ पे, I guess हाँ ये यही मिलेगी आपको. This is the equation you will get. Okay, if you perform the dot product of p1 and the p2, तो x1 square x2 square I dot I 1 हो जाता है, फिर y1 square y2 square j dot j 1 हो जाता है, स्क्वायर रूट ऑफ 2 into square root of 2 वो 2 हो जाएगा, that will be 2, and x1 y1 and x2 y2 you are going to get. तो ये वही करा है उसने, ये सॉल्व कर दिया. दिस इज द कंप्लीट सोल्यूशन. सो राइट नाउ यू आर अवेलेबल विथ सम फंक्शन, and according to that function they are saying ki this is the result which you are getting. तो कर्नल ट्रिक में
Sir,
हाँ यस,
sir, here how are we getting root 2 xy term?
root 2 xy term, root 2 xy term, I guess they are adding one more component. They're adding one more component in this transformation, x square y square we will know for the circle. Okay, and this component square root of 2xy has been coming, I guess, related to something like, uh, if I say, wait a minute, how they are added this component, something like 1 square, okay, 1 square, okay, and huh, so 1 plus 1 h square. Okay, so h equal to square. Something like a radius term. They assume that where the circle is present, and unit, something like unit distance, something like a unit distance. So that's why they are assuming somehow what it, radius has been something like a root two. Okay, so how we calculate this thing, one and one. For example, this is something unit distance, so this is root two. Okay, so that's what they are, I guess, assuming कि ऐसा कुछ है. Okay, and ऐसे ही कुछ, I think there's a considerable, because one of the case they did mention from their own end. यदि if we take from our side and if we make it as a simple, okay, just right now if you make it as a simple कि नहीं, you are going to make a circle, तो circle and with the center 0 0, तो x square y square this should be only there. ओके, लेकिन वो आर स्क्वायर भी है ना, रेडियस का स्क्वायर भी है इस इक्वेशन में, तो वो आर स्क्वायर को ही उसने कोई कहीं स्क्वायर रूट ऑफ 2xy, ये कहीं ना कहीं समहाउ व्हाट, ये ऐसे कुछ कैलकुलेशन दे डिड टेक कि वो रेडियस है ऐसा, एंड रेडियस की वैल्यू समथिंग लाइक दैट, तो वो उसको इंट्रोड्यूस कराया उन्होंने. ओके, तो कंप्लीट
Okay.
इक्वेशन हैव
So
कंसीडर्ड.
is it sure that it is the radius?
आई होप अब एक्स और वाई भी इसके साथ मिला रखा है उसमें साथ में. ओके, तो मैं अपने लेवल पे कुछ एक कॉमन अंडरस्टैंडिंग के अकॉर्डिंग आई एम सेइंग कि ऐसा कुछ है.
Okay.
ओके, तो
Okay.
द थिंग इज कि ये आपका एक्स कंपोनेंट हो गया, ये आपका वाई कंपोनेंट हो गया. ओके, तो कुछ ना कुछ वो बात लेकर चल रहा है अपने अकॉर्डिंग टू इट्स ओन अजम्पशन. ओके, तो इन दिस पर्टिकुलर नोट दे हैवंट टोल्ड अस कि what are the assumptions which they are taking while separating and while creating this circle.
Right, sir. Yes.
Okay, so we don't know about the assumptions right now. We only know the equation of a circle is x square y square, but ये भी origin नहीं है, इसका center नहीं है origin. तो in general, if I say the circle with non-origin, the equation of a circle with non-origin something like this: x square plus y square plus 2gx plus 2fy plus c equal to 0. If we know what is the general equation of a circle, यही होती है एक्स स्क्वायर प्लस वाई स्क्वायर प्लस 2gx प्लस 2fy प्लस c इक्वल टू 0. तो इतने सारा कंपोनेंट ही हैवंट टेकन, तो ये एक्स स्क्वायर प्लस वाई स्क्वायर, अब ये 2gx प्लस प्लस 2xy प्लस c इक्वल टू 0, इसी को ही कुछ ना कुछ अजम्पशन लेकर वो स्क्वायर रूट ऑफ 2xy पर लेकर आया. इट ब्रिंग समथिंग लाइक लाइक दैट. ओके, तो अभी अवर मोटिवेशन इज कि एक कर्नल ट्रिक और एक कर्नल फंक्शन व्हाट दे आर ट्राइंग टू डू, तो ये अंडरस्टैंडिंग अभी हम फोकस कर रहे हैं. ओके, और थोड़ा बहुत वी अंडरस्टूड कि यार सर्कल हमको, वी आर बीन हियर प्रेजेंट टू सेपरेट द डेटा पॉइंट्स. ओके, तो दिस इज अ ट्रांसफॉर्मेशन वी हैव टू अप्लाई. Okay, this is a transformation we have to apply. We have considered 2 points, we have applied the transformation, and we got this equation. Okay, so certainly we have to perform same activity with other things also, other transformations also, we have to apply the same things. तो अच्छा हो गया. Then what we are going to check after this transformation, if we observe the final form of kernel function, it's nothing but a circle. ठीक है, this means that we have changed our notion of similarity. That means instead of measuring similarity how close the points are using the dot product, we are measuring the similarity between whether the points are within a circle or not. ये मीनिंग कर रहा है वो. That means for create for separating the data points, they said change the theme, and instead of checking the similarity of the data points by the dot product, you say that now we are considering how the data points are coming within a circle, how the data points are coming. तो change हो गया theme पूरा. So defining such transformation allowed us for non-linear decision boundary. Obviously it's initially 2D, and now we are still linear in a original 3D space. So higher dimension. So with this dot product, dot product has created an, I guess, an illusion. It has created an illusion for you that if the data points are still present in a 2D plane, but if I want to visualize them, how they can be represented in a 3D plane. So with the help of that kernel trick and kernel function is going to work upon, it is still linear in a original 3D space. That means, understand, in this sense, defining such a transformation allowed us to have a non-linear decision boundary in 2D space. So we are making a decision boundary in a 2D space, making a decision boundary in a 2D space. Okay, and then we are considering that how it looks like a 3D. Okay, yes, any question, please let me know. Dropping from okay, fine, okay. What about others? Yes, Mr. Ahmed, any inputs from your side?
It's okay, sir. I got to the point. I'm
Okay,
following you.
okay, you're following me. All right.
Yes, sir.
So the thing is, still preparation is required, and we have to think more over the kind of task which it has been doing. Okay. In general, as per our prior discussion, it has been told that okay, if it is not linearly separated, then we need to do something else. We need to improve the dimension, and we need to shift the data points over that particular dimension. That's how it can be separated. We have seen this thing in an example that you can make a class. That means not class, a circle. You can consider a circle, and in this circle you can separate the data points by this particular way, which are not linearly separated. So circle, I have created an equation. I have written the equation of a circle. Okay, and I named it as a transformation function. Okay, and I have put the two data points x1 and x2 into this transformation function. Okay, and I have calculated the dot product of it. Okay, and after calculating the dot product, I am saying that let us map that if this point is present in a 2D plane, how this point looks like when it should have to be present in a 3D plane. Okay, so ultimately it shows that now you are having a higher dimension. You are having a higher dimension, and you are separating your data points according to it. So this particular transformation will actually looks like, okay, not here, it actually looks like, okay, okay, we've seen that how it's gonna look for you, like this. Okay, like this, it will look like. So we have performed transformation of the data points. Okay, here the transformation occurred of the data points. 2D represented as 3D, you know 2D representation, and has been now as a 3D, 2D to 3D. We have transformed the data points by just creating a circle. So now you can say it, they can be classified. You can see it can be classified. I can make a plane and I can classify it. Not a line, obviously. In 3D there will be not a line, because you've already also learned one more concept. One more concept. What was the concept? If you are having n dimension, you can make a hyperplane of n minus 1 dimension. Did you remember this thing? So
Yes, sir.
right now you are having 3 dimension, so you can make a hyperplane of 2D. So 2D will obviously a plane. So I'm with the help of a plane now I'm dividing these two. So how it looks like it. Now let me again show you. There is a one GIF which has been present in my notes. Yeah, here it is. Yeah, in 3D, if you want to separate the points on 3D, this is your hyperplane look like. Okay, so you transform the data points from 2D to 3D, and this is how you can do. This is how you can achieve. Okay, so you have to apply the transformation. and transformation will be according to the way or the approach. You have to look out for the which function is better to perform the transformation. So we are available with certain kernel functions in our svm. Okay, and these are the kernel functions we have studied about them. Okay, these are certain kernel functions: radial bias, sigmoid, 3D polynomial, second degree polynomial, and these are their equations. So when you are available with the svm, when you are going to apply svm, you have to put the value of these kernel. For example, if with one of the kernel as a hyperparameter you're not going to get the good result, then you have to change that. You are either you are going to use linear, either you are going to use radial bias, either you are going to use something else. Okay, then you have to check the accuracy, because no one, okay, it's difficult for us how the data has been present. All right, so these things which will come up when we are going to do the practicals, and then it will help us in learning and understanding. Okay, so what is the next things? Brief summary. So let us suppose we are having each point xy coordinate present in a 2D plane. Okay, we project the points on the 3D plane. Okay, and here is the transformation function: x square y square under root 2xy. Okay, points which are having high value x dot y would move upward along the z axis. Okay, and we are going to find the hyperplane in 3D space that will be perfectly separated the classes and form a kernel function indicates the hyperplane would form a 2D space, a circle in 2D space gives us a non-linear decision boundary. So ये transformation only is going to create your non-linear decision boundary. This kind of transformation is going to do it. So these are summary points which has been happening. So consider the data points, take them as a vector, calculate the dot product of it according to the transformation function, and shift the points according to the transformations. Okay, that's what we have to do from 2D to 3D. Representation of 2D points to the 3D points. That's what we have to do. Okay, so right now you are having consideration of a circle. Okay, so this is the equation which they have taken. Okay, now what is there? By embedding the data into higher dimensional feature space, we can keep using a linear classifier. We can keep using a linear classifier. Now what this mean? What this mean? A caveat here is that these transformations could increase the feature space drastically and increases the computational cost. Is there any way to reduce the computational cost? What is the way? Okay, see, we did started. We said that we are going to perform the transformation and we are going to reduce the computational cost and we can classify. That's what we have told. Okay, but still they are mentioning that these kind of transformation could increase the features. Obviously, dimension is increased. Now because of this dimension increase, your points has been shifted. Okay, so there is still some computation has been there. Then only this thing is when what is the computation? You perform the dot product, and then only you have transformed the data points according to the transformation function. Okay, so what can be done? What they are trying to say? They are saying that, okay, let us reconsider. This is our equation: x1 square, x2 square, y1 square, y2 square, 2x1 x2 y1 y2. And then they generalize it. Okay, like this is a square b square, a square plus b square plus 2ab, I guess. And this is the formula: a plus b ka whole square. Am I right? है ना? A square plus b square plus 2ab.
Yeah, right,
है ना?
sir.
So
Right, sir.
a plus b ka whole square. So they are saying, okay, p1 p2 ka whole square. They are saying that okay, this is the kernel function, so it's a p1 p2 ka whole square. Okay, so the value of kernel function, the similarity between the points 3D is just a square of the dot product of the 2D space. Okay, so the 2D space का dot product, they are saying it's a square of the dot product. तो ये तो dot product ही था ना. This is the dot product. So I am considering one point p1, I am considering another point p2. तो इन दोनों के dot product का square. इतना काम है. This is the work which we have to do. ये बोल रहा है. So the value of kernel function is just a square of the dot product of the data points which are present in a 2D plane. So whatever you are going to calculate a dot product of p1 and p2, and whatever be the result which you are getting, just square it, just square it. Okay, so अब ये हुआ कैसे, क्या कहना चाह रहे हैं वो, how this thing has been achieved, what happened? So the reason for this, we choose our transformation function very wisely. We have to choose this transformation very wisely. तो अभी I don't know actually that's the case. ये तो है actually. This is the game, that how to choose a kernel function. This is the game. Either you are going to choose linear. If with the linear I'm not going to get the good results, obviously I need to perform hyperparameter tuning. Then I will be definitely choosing some different kernel. I can take this radial bias, and I can take any polynomial kernel, and then I can put see that what is the way that data points can be classified correctly. So I need to perform hyperparameter tuning, and then I'm going to get this thing. Okay, so these are the things which we have to apply. All right. So and it will help in curbing the computational cost. That's what they said. Further कोई computation no need to done. They said कि it's a dot product, and dot product का overall square. Okay, so whatever be the result I'm getting now for the dot product, just to square it. That's what we have to do. So it will automatically curb the computational cost which you are expecting. Ki sir, transformation was done, and sir, we have created an additional dimension, and we have shifted those points to that dimension. These are the things ye what we have approached so far. So they are saying hard, okay, fine. But the thing is ki actually I can put this equation in this way also. Okay, so it will help us in reducing the computational cost, because calculating a square is not a big deal of the dot product of two vector. This is how we can do. So this is your soft margin and kernel trick and kernel function. I know that things are complicated, not easy. Okay, but we have to learn, we have to understand. Okay, that's why I'm taking enough time for explaining. Multiple times I've explained, this is how we have to solve the maths for SVM, and these are the things happening behind the SVM. Okay, now what are the assumptions before you are going to apply support vector machine? You are going to apply this algorithm, you study the classification case. What are the assumptions? Data should be linearly separable for linear SVM. If you are using SVM and you are taking kernel as a linear, so we are having assumption that okay, data is linearly separable. Okay, for kernel selection for non-linear SVM, again, if the data is not linearly separable, then we need to separate it by some another kernel. We have just seen above that we are going to map the data into the higher dimension space. तो मैपिंग कर रहे हैं हम, मैपिंग. Okay, your data is present according to what has been there actually, but according to your maths, you are applying maths over that data, and you are shifting the data points to higher dimensions. Okay, so ek ye this is the kind of illusion which you are creating over your data, that okay, this is how my data looks like in 2D, and now if I apply this transformation, this is how my data looks like in 3D. Why the reason? Because then this is the way only you can separate it. Then we can check the performance of our model, that how it is working. So you have to select different non linear kernel. Okay, and then you need to check which one is giving you good accuracy. If linear is also failed, if non-linear is also failed, then obviously your model is not working good here. Just change your model and try another for classification. Okay, then feature scaling. See, SVM is sensitive to scale the features.
One question.
Hmm.
I mean, SBM, it's actually deal both of
Regression
classification.
classification, both.
Okay, so next question, like when I mean, in case of data is like non-linear, then we can use like map function. I mean, do you example like because we know that if we apply in the non-linear data through the standardized or normalized, then that should be like linear or use like log or something else. But in here, like map used
Mapping. See,
for
mapping is actually a transformation. Mapping is a transformation. Okay, that's what we are seeing. For example, this data point is present in a 2D plane. How it looks like in a 3D plane. That's what we are doing with the help of transformation. That's the deal. So it's
And
present.
by
Hmm.
default, support vector sub SVM,
Hmm.
which I mean, is it set up in linear or non-linear
Huh. See,
to be fixed here?
in general, we are having linear SVM. In general, we are
Okay.
saying linear SVM. If you put, there is a hyperparameter. For example, you need to put a kernel function. If you put kernel, if you put a kernel function here, for example, RBF, now it will behave non-linear. Okay, you have to put, you have to kindly do check scikit-learn official website for the SVM. They will tell you about all the hyperparameters which are available. So here we can decide the kernel. We start with linear thing, we try to solve with the linear thing. If you are going to get the proper results, good accuracy, fine, that means your data is linearly separable. But if it is not, you are getting low accuracy. In that particular case, you have to change your kernel, and then you have to try with different kernels, and then check whether accuracy is going good or not. If it is still not going good, then obviously your model is not being supported over that particular data point. So that's what we are learning, assumptions. So assumption number one is linear. Try. If it is, then proceed for the non-linear. If it is not linear, then non-linear. Also, you need to perform feature scaling. You need to scale your
And
features.
next
Hmm.
question, like
Hmm.
in case of like kernel,
Hmm.
is it like same all of algorithm like linear, polynomial, Gaussian,
Uh-huh.
and
Yes,
eternal? I
all
mean, is it?
all other types of kernel, all are the types of kernel. So kernel can be linear also. It's a simple case. Linear kernel is a simple case. Rest are complicated. Okay,
Yeah, non-linear.
rest are non-linear case. This is linear is a simple case for linearly separable. Okay, so you need to try and test your SVM according to the kernel. Okay, feature scaling should have to be done. You have to normalize your data. This is what you have to do to sort out the dominance of some feature on another feature. We need to normalize our data. For binary classification, SVM is primarily designed for binary. See, every algorithm says we are good in binary. So SVM is something, if you are having a binary classification, you have a full rights to use SVM classifier, and hopefully SVM is going to give you the good results. Okay, so for binary classification you can do it. For multi classification also you can extend SVM, one versus one or one versus rest. This has also been possible. One on one has also been there, and one versus rest is also been there in case of SVM. You can use it for multi classification also. So binary is best, and rest also is been applicable. Multi class classification has also been applicable with the SVM. Limited noise and outlier. Okay, assumes that the data is mostly clean. See, that is why you need to pre-process your data properly, and you need to remove the noise and the outliers. Then apply SVM. Don't apply SVM with outlier. Then वो misclassification पे हो जाएगा, and error ज़्यादा, there will be much more error, and because much more error your accuracy will dip. Okay, so it's limited noise and outlier should be there. Homogeneous data. So
So,
homogeneous, huh,
I mean, a binary class, is it like this
0
class
1,
is like
0
feature?
1,
Yeah, I know. Yeah,
A
target
and B.
features.
Target
I mean,
target variable. Target
uh,
variable is either 0 1 or either A or B.
yeah, got it. Yeah.
So homogeneous data. So homogeneous data, what does this mean? Assumes that the data is roughly homogeneously distributed across the classes. Okay, so not heterogeneous, homogeneous, same. That's what we call as homogeneous. Okay, so it assumes that the distribution of data is homogeneous in nature. So if one class has much fewer sample than the other class, it will affect the balancing between maximizing and minimizing the margin. So and it will lead to misclassification. So आपको पहले data balancing it is required. You need to balance the data, then only you are going to apply the SVM. Don't do that imbalanced data. Don't use classification over imbalanced data. तो ये SVM काम नहीं करेगा. It will not work properly, or over data imbalancing. Balance it and then use. This is the assumption. Low to moderate dimensionality. Low to moderate dimensionality. So SVM can. Uh,
Yeah, one question, like SBM, like this. Would you go a little? Yeah, SBM homogeneously. I mean, I think it should be it should be acceptable for all of algorithm, not like SBM. Like
It's been acceptable for all. Okay, it's acceptable for all. Right now, as we are talking about the general case, we are talking about SVM, so that's why I mentioned it's
oh
a
yeah, yeah.
it's a see, data imbalancing is obviously an issue. If your classification and if you are having unbalanced data, obviously the dominant class is going to take the most of the credit. So we need to balance it. That's the theme. That's why we apply smart algorithm. Okay, and we balance our classes, and then only we are going to apply the algorithm. That's what we
Yeah.
do. Okay, so here also same thing is applicable. So low to moderate dimensionality, that means SVM can become computational. ये तो होते ही है. Computationally expensive. See, if you are having a large data, okay, so obviously SVM is computationally expensive. It will take long. And if you are doing hyperparameter tuning of SVM, then you should have good memory income. Obviously, yeah, it will take hours also to solve with SVM. It's not an easy. If you are having a huge data and you are performing hyperparameter tuning, obviously it will take a lot of time. It is computationally expensive. This algorithm is computationally expensive, sure, because you have seen the kind of approach this algorithm follow. It's expensive. Okay, it will take a lot of time to solve. So you should be prepared. That is why it is called as curse of dimensionality. So if someone say, which algorithm is having this curse of dimensionality? SVM. Okay. So and choice of regularization parameter C, that means na that parameter which decides how should be your margin. So this C controls the trade-off maximum. So you should have to check out what should be the value of C. Again, it's a hyperparameter we have already seen. Okay, and we have seen what is the issue between C and M, margin and the C. Okay, so this regulation parameter. Okay, limited training points, unbiased representation class, and okay, sensitive parameter tuning. Yeah, that's we have seen. Okay, so not that much uh, points which will put in. Okay, everything has been discussed. Okay, so what's present? Yeah, ask the question. Anything you want to say? Yes, Ahmed.
Sir, my question is like, can you give some shade how this super vector machine is different from like perceptron? Like this is one of the question most of the time we got in like
Okay,
interview.
okay, how it is different from
Perceptron.
perceptron?
Yes, sir.
Okay, so what is this perceptron is? If we say perceptron, perceptron.
Yes, sir.
So again we are relating it with the neural network. Is it? Is it? Are we relating it with the neural network?
Like I have some idea about like the perceptron. Like this the super vector machine have
Huh.
better in perceptron we will get infinite
Huh.
like classifier, but
Hmm.
in super vector machine we will have like optimal
Optimal.
classifier.
Huh. Optimal.
Yeah, like in
We are
that
our main goal in SVM is to find the optimal margin. That's what our goal is, to find the optimal margin. That's why we called it as, okay, it's a classifier, optimal margin, and we have used that so far generalized equation just to find optimal margin only, just to find optimal margin. That's our goal. We are going to create a decision boundary. Now, the question which you ask, do you create any decision boundary or do you look out for any optimal margin perceptron? Do you perform this activity in perceptron?
yes in perceptron like we have many like decision
Huh?
classifier, but in super vector machine we have like to choose the optimal one, like
Huh?
but in SCVM we have some assumption to do that. Like I didn't get how mathematically this SCVM improve the perceptron algorithm.
See, See, perceptron, as I already told, that you right now you're talking about a neural network. Okay, for perceptron you're talking about a neural network, and actually you are talking not only neural network, you are talking about a single layer neural network. You're talking about this thing as a single layer neural network.
Yes, 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 yes,
Perceptron, है ना?
yes, sir.
That's a your
Yes,
perceptron. It's a single layer neural network. So obviously you are having here the neurons, है ना? In a single layer, you are available with the neurons. Now, how this is separated? Obviously, for example, you are having an input layer. You are available with the neurons. You give data points to it, है ना? You are going to give input features. You're going to give the features here, x1, x2, x3, all these features are been given here. Then what you are available? You are available with activation function. Activation function. Now you will say, sir, neural network we are having activation function, and sir, here you are having kernel function. So things are getting similar, sir. Am I right? Here you are having kernel function, and here we
yes,
are
sir.
having activation function. And also, sir, we have seen in neural network the activation function. There is one of the function is sigmoid, and sir, you have also told that there is a sigmoid also present in this SVM. We have seen sigmoid kernel function. No, sigmoid function, kernel function. That is, so things are getting similar. Things are getting similar here. Okay, but the working approach is different in case of perceptron and in case of this thing, because you know what we do here we do supply the value to these things, okay, to the neurons, okay, and then we are having activation functions. We are having activation functions here. Okay, we can have a multiple activation functions we can use, for example linear activation functions or something like that. And with and these activation, one more thing, again that's a very good question which he has asked, because you know what happened, we are having wx plus b also, the same kind of equation which is used in the neural network. Is it right? Same
Yes,
thing
sir.
we are
Yes,
going to, so equation is also same. There you are saying in neural networks, sir, this is again weight and the bias which we assign to the neuron. Weight and the bias here is what we assign to the neuron. And here weight and bias, they represent a hyperplane in my case. So weight and the here this equation represents a hyperplane in my case, and this is the equation which we say it's an activation function here. This is activation function, so that's the difference. Here wx plus v is an activation function which will help you in performing the classification, and here wx plus b is an hyperplane for me which will help me in performing the classification. Okay, so things are getting very much tight and somehow what similar also. Okay, so definitely we can have a good discussion over this topic, and he has asked very means in depth. He is asking, sir, everything is going to be similar. Machine here also you are saying is a machine, and neural network will also behave in the same way. We are having layer, we are having neurons, we are assigning, and every neuron are assigned weight and the bias. Sir, here also a weight and the bias, and you are having an activation function wx plus b. Here you are having kernel function. Same concepts are been working on. So how they are different from each other? Very good question. So this is certainly which I marked initially, that okay, this is a sigmoid function, and now you're representing as a hyperplane. One is a sigmoid function, one is the hyperplane. In SVM we call it as a hyperplane. In neural network we are called it as a sigmoid function. Okay, we are going to apply this weight and the bias, and we need to do this in case of neural network. We'll discuss more on this in the next class, definitely. Okay,
okay, sir.
fine. Let me stop the recording. Anything more you want to say?